Hi everyone, this is Aurora with Supercharged Science, and we are going to do a hands-on science lesson just in civil engineering today. So if you like this and you want more, you want to go to my website, which is www.superchargedscience.com, and take a look at, go to superchargedscience.com/easy, like wow, that was so easy, and take a look at the video that's there, and I will show you step by step how you can teach science to your kids, and it's not a headache, it's not a hassle, it's easy, it's fun, they're engaged, and they will learn more science than they ever have before. So it's totally fun, and go to superchargedscience.com/easy. Okay, so for today, I'm going to get some slides ready for you, and I'm going to share them with you. We're going to do a little mini science lesson. We've been doing these for I think about 2 weeks. We've done astronomy, two astronomy, one in solar and one in planetary. And we've done a number of other topics, and so today we're actually going to talk about application. The difference between engineering and, for example, physics is much more theoretical. Engineering takes those ideas and concepts from physics and puts them into a usable form. And so that's what we're going to talk about today. So I have some slides to share with you. We'll be together for about 20 minutes. If you know of anyone who would love this, let them know we're doing this. Invite them in. Totally free class. As I mentioned, I actually put together even more lessons that you can do. This is just going to be a small snippet from my huge online science program. So if you have questions at all anytime during this little mini science class, just go ahead and let me know by putting in your comments or typing it in the comments section, and I'll be checking that to see if you have any comments. Okay. So here we go. Now, if you're listening to this on the podcast and I'm talking about some slides, you might want to go to the original Facebook Live, just to let you know. Okay, so we are actually going to do a little mini class in civil engineering. Let me share my slides with you so you have those. Here we go. Okay, so did you know that every time you take a shower or you drink some clean water, you flip on the lights, you open up the fridge, you drive to school, stop at a stoplight, or even take the bus, maybe you're on an airplane on vacation, or you throw your soda can in the recycling bin, somehow there was a civil engineer involved somehow. So I'm going to give you a little sneak peek of what it's really like to be a civil engineer, how that field got started, and how it's absolutely everywhere you look. Now, civil engineering covers everything from building bridges to skyscrapers to working through several design challenges, especially when they're in college. And we're going to look at real projects, and we're also going to look at different types of engineers. Now, the cool part about this is there are if you've got a kid who's crazy wild about science and you're thinking, yeah, what kind of future is he going to have? There are four different types of engineering majors that make up 2/3 of the engineering market. And in years to come, the engineering market is actually going to grow and expand, and civil engineering is the one that's expected to grow the most. And so it's just simply because there's going to be more people and more, we're going to need more buildings and more structures. So this is a surefire way to, if your kids love civil engineering, if they love the kind of things we're going to talk about here in a minute, this is a great path to set them on to get going. Now, if they have a science and engineering mind, this is a great thing to expose them to see if it's something that they're interested in. Okay, so let me share with you some basics. So what do you think a civil engineer is? Just take a wild guess. Tell me out loud, type it in the box if you'd like. What is a civil engineer? I'll give you 10 seconds. Tell me, what do you think it is? What do they really do with their day? How do they spend their time? What do you think? So according to the U.S. Bureau of Labor Statistics, civil engineers, quote, design, construct, supervise, operate, and maintain large construction projects and systems. Yeah, well, what is that? Okay, so basically, a civil engineer designs and builds things like bridges, dams, roads, buildings, airports, tunnels, and systems for things like when you flush the toilet. It's actually one of the oldest branches of engineering. You know, when people first started living in permanent settlements like cities, they started to shape the environment to be what they needed. Now, early engineers built things like walls and roads and bridges, and they also did things like dig wells for water and make irrigation ditches and trenches. But as these settlements got larger and formed into towns and cities, people needed clean water. And also a way to get rid of waste and real streets that we could drive on, not just cobblestones. And so something that everybody could use, and that's where civil engineers come in. So what's the difference, you think, between a civil engineer and an architect? Sometimes it's a little fuzzy. They're both build things, right? Okay, so an architect focuses on the aesthetic principles of design. So in school, you'll actually take more art-related classes and fewer engineering and science-related courses. Now, civil engineering focuses more on the science and the engineering itself. So in college, you'll take fewer art classes. You'll spend more time with engineering and physics that normally you would have if you were an architect major. It's also considered more difficult than architecture because civil engineers also build things architects don't, like hydroelectric dams, canals, roadways, and structures that are useful and functional for the community and don't have to necessarily be aesthetically pleasing. So imagine, how would you figure out how to get clean water to your house from like hundreds of miles away? How would you build roads and bridges through mountains or across rivers? If you've never seen a road or a bridge before. Well, 1,500 years ago, the Mayans of Central America built drainage ditches and irrigation canals to move water to their farms. And before that, the Romans in Europe built aqueducts to carry drinking water from the mountain springs to their cities. Now, the Chinese, they designed irrigation systems to control floods that are actually still working today. So ancient civil engineers, they built roads for the Roman Empire. They constructed the Great Wall of China, the cliff dwellings at Mesa Verde, the Mayan ruins in Copan, and these structures, they're still standing today. Many people actually will travel from all over the world just to look at them and be totally amazed. I mean, these people didn't have internets, computers, big construction equipment to help them design and build these things. They didn't even have universities with college majors the way we do today. So I want you to notice something in these 4 slides. What is the stuff made out of? What did they build their designs out of? Wood? Steel? No. What did they use? Yeah, they used stone, right? Why did that? Well, what do you think they had a lot of that was cheap and easy to get? Yeah, rocks, right? So a lot of ancient structures that are still standing today and didn't erode away, they're going to be made of stone. So you've probably seen pictures of the Great Pyramids and Stonehenge. These were built by ancient civil engineers, and scientists today still have no idea how they did it without modern heavy equipment like cranes and excavators that we understand. I mean, how would you move blocks that are 30 feet long, weigh 25 tons each from a dig site 20 miles away? For comparison, it would be like taking all the wheels off of 2 fully loaded, full-size school buses and then trying to move them. So how would you do this? So that's what ancient civil engineers did, right? Okay, so let's take a look at this. Today, civil engineers build projects like this one. Point to the ones as I call them out. See if you can figure it out. The Brooklyn Bridge, this one was designed by John August Roebling and his son Washington. The Golden Gate Bridge, the red one, designed by Joseph Strauss and Charles Ellis. The Hoover Dam, which was designed by John Savage. The Panama Canal, which was designed by John Frank Stevens. And the Eiffel Tower, which was named for its French civil engineer. Did you get them all? Did you notice how a lot of these were built by people? The first name was John. It's good that most civil engineer projects don't carry the name of the buildings and designers' first names, right? We have a lot of structures with the same name. So civil engineers don't just build things. They also research and test how well materials can withstand things like earthquakes. 50 earthquakes occur every day in the world somewhere. They work on bridges that can detect problems and send emergency alert warnings when they're in danger of collapsing. Civil engineers also work with artists to help preserve historic art structures like the Wyatt Towers Monument in Los Angeles. So if you want to be a civil engineer, you'll need to take college classes in things like physics, math, geology, hydrology, study of water, materials, construction, machines, and a lot more. So you'll not only need to know what to build, but also how to build it. You'll find civil engineers, in civil engineering, you're going to help select where to put the project, which materials to use and where. You're going to work with computers to design the models and get the kinks out before you actually start building the project. And most engineers, typically they're stuck in an office behind a computer or in a lab doing experiments, both of which are cool. But civil engineers have something different. They actually get outside and on the construction sites so they can make sure the work is done right and solve issues that came up that nobody could account for. Here's some of my favorite construction issues that actually happened. You want to see if you can figure out the problem with each one? Okay, here we go. What's wrong with each picture? Do you notice anything unusual? I don't know if you can see the one here in the roof, but the chimney is going through and there's a window here. Yeah, do you notice anything a little unusual? Yep, it's missing the window for the balcony or the doors. Yeah, how would you get to this second flight? I don't know. And if this is a wheelchair ramp, I think we have a problem here, right? Okay, how about these? I mean, how do you park your car when the garage is on the second story? So it's important to stay on top of things. I mean, everybody makes mistakes, right? We're all human. So it's important for civil engineers to stay on top of things. So this is a skyscraper in Dubai. It was completed in 2009, and it's the world's tallest skyscraper. It's nearly half a mile high. It has 164 floors, 900 apartments, 304 hotel rooms, 58 elevators that go about 22 miles an hour. Now, when we first started building these things, early skyscrapers were dark and small because the walls were thick because they were made of heavy stone, right? That's all they knew how to build. And buildings could be up to about 10 stories high, but the rooms were still so small and they didn't have a lot of windows because when you have a window, it's not as strong, right? And the first elevators were actually invented to make it easier for people to go more than 4 or 5 flights of stairs. Now, what do you think one of the biggest concerns is when it comes to skyscrapers? Actually, it's wind. Wind is one of the biggest issues with skyscrapers. Tall 1,500-foot buildings are going to have to be 50 times stronger than 200-foot buildings, right, to be able to withstand that wind that comes along. And the wind is different speeds depending on how high you are above the Earth's surface. So imagine now you're a real civil engineer and you're walking into your civil engineering office one morning and you find out you have 3 skyscraper emergencies to sort out right away. Okay, so here's the first one. You ready? This one is in Chicago, Illinois. It's a very old 5-story wood apartment. That burned down to the ground like months ago. And since then, it's already been decided to rebuild it as a 50-story apartment building. Okay, so it was a really old 5-story wood apartment building. It was totally destroyed. They're going to replace it with a 50-story building, right? You, the civil engineer, need to tell the construction crew the type of material to build the new one out of. Now, this new building is a lot taller than the other one, and it's going to be heavy. So with the lower level, there's going to experience a lot of tension or compression, do you think? Well, hang on. What's tension? What's compression, right? Okay, so if you've ever teetered on the end of a diving board, you know that the board flexes under your weight, right? The heavier you are, the more it bends. Okay, so the top of the board gets slightly more stretched than the bottom. So the top was going to experience tension, that pulling force, and the bottom is going to experience like a push, okay? So that's going to be under tension and compression. So if you actually take a pencil, let me see if I have a pencil. If you actually take a pencil here, or a craft stick or a popsicle stick, and you can bend it along your fingers, but not too far. Notice that it bends quite a bit without breaking, okay? And you let it go, and it snaps back to its original shape, and you bend it, and it will start to kind of arc out, right? Wood is fairly elastic, meaning that it can bend quite a bit before it actually breaks. So this comes in handy when you happen to be like a tree, right? And it's a really windy day, so most trees will bend and sway in the wind, right? And so that's a good thing to be if you're a tree. So now if you want to go ahead and break your pencil, you can. You just kind of go ahead and break it, and you notice, look at the part that just broke, and you may notice that one side looks a little different than the other. Let's see if I have a slide of it here. Sort of. I have a slide here. It's a little closer than I could show you. So notice that it's going to break differently on the other side. So tension is when things get pulled apart. Compression is when they get squashed back together, okay? So keep these 2 ideas in mind. Now let's go back to our skyscraper puzzle. Okay, so the lower levels of a huge skyscraper, are they going to be under a lot of tension or a lot of compression? A lot of push, right? A lot of compression. Okay, so what do you think we should use to build it? Should we use stone? Should we use steel? What do you think about stone? Let's think about stone for a minute. It's strong in compression, right? It's cheap. Will it burn in a fire? No. But what's the problem with stone? You tell me. You ever tried to move a big rock? It's heavy, right? And if you try to build a 50-story building, let me show you my slide, a 50-story building out of stone, it's going to sink right into the earth. What about steel? Steel can be stretched and squeezed and twisted and moved around without breaking, and it's usually a good choice for tall buildings. The Sears Tower in Chicago. See that building with 2 antenna things sticking up out of the top? Okay, that's actually made entirely out of steel. This one right here. But steel is good at normal temperatures, but it melts at about 700 degrees, so it's not a good choice if you're worried about a fire. And your boss now wants a fireproof building, so you can't do just steel. So how would you fireproof steel to slow the heating of the beams? Well, what about concrete? Steel reinforced concrete, see the picture of it there on the lower left, is the best option because the steel is super strong. It doesn't break easy. It's super strong in tension. You can pull it and it doesn't break. Concrete is super strong in compression. You can squish it without a problem. So together, you can squeeze and stretch this building without actually breaking it. Phew, you did it! Challenge number 1, totally solved. It's out of the way. So you go to the construction company, you tell them, hey, this is what you want to make your building out of, steel reinforced concrete. Okay, you ready for another challenge? You've got enough in you for 2 more? Okay, so these are all, by the way, real world problems that actually happened. So here's another one. Okay, so here's the second one. In New York, there is a 300-foot tall building that is currently still being built, and it started to sink because the soil was too soft on one side and it was rock hard on the other. And your boss is worried, it might wind up looking like the Leaning Tower of Pisa. See it there on the right? So he wants to know, should we continue building it? What should you do? Okay, so your options. You can stop building. Okay, so when you stop building, you could use a chemical glue, mix it in with the dirt to firm up and harden the soil. Or you could dig deeper to strengthen the foundation. Which one should you do? Which one of those 3? You could just stop building, scrap the project. You could somehow chemically change the soil, or you could dig deeper. Which one? All right, well, let's think about each one. If you stop, you've had to spend money cleaning up the project that you already started, and then you still have to build it somewhere else. Now it's totally out of your budget. You don't have enough money to continue this. You're already out of money. Okay, so that's not an option. What about the glue mix-in? Well, you could use glue, but it actually turns out when you research it, it's really expensive, almost as much as the entire building construction cost itself. And you realize, all right, fine. Don't have enough money for that one. So what else should we do? How about digging? Well, when engineers have to build on sandy or soft ground, they'll actually dig really deep to find the kind of soil that can support the huge amount of weight. So the ground beneath the 1,500-foot tall John Hancock Center in Chicago, that tall building in the middle with the big X's going up it, that was actually, this is the building we're talking about that had this problem, and they had to dig and dig and dig until engineers hit bedrock about 200 feet below the surface. So that's how much support this guy had. Yeah, doesn't this look like the heel of a high heel shoe for a woman, right? You're putting all that weight onto a very small footprint, so you have to be very careful about what you're putting underneath, right? You ever seen women like in really tall high heels and then they try to like walk on grass or something and they totally sink? That's the same idea, just on a much smaller scale, right? So, but if that the high heels are going to be going clip-clop on the concrete, it's no problem, right? Because it's like solid rock. Okay, so what are you going to do? You're going to tell your boss, hey, you know what? Just keep digging until you get to the right type of foundation that we need before any more work is done on the building. And your boss is like, great, let's do it. Phew! Problem number 2, out of the way. You ready for problem number 3? Okay, here we go. Problem number 3. Now again, this is Aurora with Supercharged Science. If you just joined us, we are doing an in-depth look at civil engineering, what it is, and how to get your kids excited and interested in it. Projects you can do at home, giving you a real taste of real hands-on science. And so if you like this and want more, go to my website, www.superchargedscience.com/easy. Like, wow, that was so easy. She's going to teach my kids all this science stuff for me. My kids are going to turn around and teach me science. This is awesome because I didn't have time or skill to do it. So go to www.superchargedscience.com/easy and your kids can continue this particular lesson. This is just a small snippet from my huge online science program. Okay, so let's go to challenge number 3. You ready to see this one? Okay, now again, all of these actually happened. So here's the third challenge. San Francisco, California. a 75-story steel reinforced concrete skyscraper, so the one we thought of for challenge number 1, it's about to collapse because it was designed wrong. And inside are hundreds of apartments, shops, and actually a movie theater. And the owners want a lot of open space and huge windows on every floor. Okay, so what are you going to do? So basically what's going on is they've got a building. It wasn't designed for what the developers want to do. So what they want to do is they want to make a big movie theater, so have a big open space inside and really big windows. So that's going to take away from your structure. So you've got to take a look inside and see what type of structure we need to put in there in order for the building not to fall over. Okay, so first off, you could put columns all up and down the entire building, right? You could just put, you could just lace this thing inside, but that's going to be a problem if you want it. This is option number 1. That's going to be a problem if you want big open spaces, because you've seen those buildings where you walk into a big open space, but there's like columns everywhere. That's proposal number 1. We just put columns everywhere, kind of make them pretty or decorative, but there's going to be great big, structures all over the place, right? It's great for playing hide and seek if you're a kid, but if you want the feeling of wide open space, you're not going to have it. Okay, number 2, if you do, number 2, you could put a core of steel beams up the center of the building and just put like a core of them. Or you could encase the perimeter in a cage network of steel beams and bars. Which one would be the best? Okay, so if we do option 1 and run beams all up and down the entire tower, it's going to be very dark inside and not have a lot of space. There's going to be like support pillars everywhere that we just talked about. And it's expensive. That's a lot of material for that size of a building. If you want a movie theater, what's that going to be like with like beams all over the place, right? You probably can't see the screen very well. Okay, so option 1, it's not an option. It's out. Okay, what about beams just on the outside? Like a steel cage around the whole thing, like option number 3. Okay, well, that's inexpensive, right? Because it's not as much material. It's effective, but are the owners going to like it? No, because they want a lot of big, open, airy windows. And now you're going to cover them up with this extensive framework like a shell or a cage around the outside of the building. Okay, so they're not going to go for that. Scratch number 3 off your list. Okay, number 2. A core running up the length of the building that will form a rigid backbone with plenty of space for windows, apartments, and a movie theater. And it will provide extra support in high winds, which is really common for skyscrapers. And as a bonus, you can actually put an elevator in this core that goes up and down, right? That's where elevators usually are. The Chrysler building here in New York has an inner core. That's the building you see here on the right. Okay, so what are you going to do? You're going to go back to your boss. You're going to go back to the owners and say, you know what? My best recommendation, you're going to put a steel core right through the middle of that building and ask them, hey, how many elevators would you like to stick in there? That way they're not focused on the other problems, but they're focused on, hey, I have another choice to make. All right, so how did you how did you like that? Okay, but there's a problem with that solution. San Francisco is known for its earthquakes. Do we have a problem? Yes, we do. So go back to the drawing board. Hang on a minute. I said it was made in San Francisco. So how do you want to reinforce that building in addition to the inner core of steel that we just talked about so it doesn't break when it shakes back and forth? Well, you go to your team of engineers and they come up with 3 more ideas. Ready? First, they said, well, you could have crisscross diagonal braces up the center core, like a power line tower, or that you see here, crisscrosses. This is a power line tower. Okay, or you can add long support beam arms out of the outside of the building to prop it up. Or another idea, well, why don't you put solid concrete blocks up the shaft so it's more like a rigid backbone? All right, well, which one of these is actually going to withstand the shaking of earthquakes? Okay, so the power crisscross idea is okay, but steel's expensive, and actually after you do the math, you find, hey, you know what? It's not going to actually add that much rigidity for the money as maybe another option. So it's okay, but there might be a better option. Okay, so the long arms, what do you think about this? How attractive is that going to be? Not very, right? If you have all these long arms propping up your building. Also, they're attached to the ground. During an earthquake, does the ground shake? It sure does. So sometimes the ground is going to shake in the opposite direction and the wind is going to pull the building up and down instead of supporting it. So this is actually going to make the problem worse. Okay, so the last one, the concrete backbone. Let's look at that. So solid concrete walls, we call them shear walls. They have a lot of stiffness, which means that as the ground shakes, the shear walls keep the building solid and strong because they are stiff in the horizontal back and forth direction. So the first Interstate World Trade Center in Los Angeles, California, this one you see here, has solid concrete core up and down the center of the building. So it can withstand an earthquake up to 8.3. Isn't that amazing? All right, so what are you going to tell your boss? Yep, you're going to tell him you got a solution, you got that inner core, and you've also got these big blocks that are going to provide the horizontal stability that you need when it starts shaking. Phew! You did it! Yay! So I know we just focused on skyscrapers, but there's a lot more that we can talk about. And for example, we can talk about bridges. We can talk about materials that you make things out of. You can talk about different types of bridges. You can talk about where to put bridges. You can talk about so many more things than in a for civil engineering. You can talk about tunnels. I'm looking for my tunnel slide here, and I'm not having much design. We also talk about the different types of engineers that you have to work with when you're doing a design. It's not just all civil engineers. You're going to be working with mechanicals. You're going to be working with all other types of engineers to try and solve problems that come up. And there are all kinds of cool hands-on projects you can do with kids. You can actually use a single sheet of paper that can lift several pounds, tens of pounds here. I think he's got 1, 2, 3, 4, 5, 6, 7 textbooks that are supported by a single sheet of paper. So that's a cool design project you can do with your kids that's easy. Let me show you another one. This is an easy one. You can do this is actually my kid here. Where is he? I saw a picture of him. He just snapped his photo as soon as he designed it. Here it is. You can take some popsicle sticks and have them design a bridge. Where did he go? There we go. Okay, this one's mine. This was Joseph. And so this bridge that he created actually holds up 50 pounds. And if you want the step-by-step instructions on how to do that, you want to go back to my video library archive on Facebook. And I actually did a whole Facebook post just on that, on how to design it. And I did step-by-step instructions. So I know we went a little bit over 20 minutes. We're at like 26 minutes. I hope this has been helpful. If you've enjoyed this and you want more and you want your kids to be exposed to this type of science, remember, science and technology is not going away. In fact, some of the best jobs, some of the best paying jobs, and the happiest scientists and engineers are in these types of jobs in the future. Civil engineering has a really solid future because we're going to be needing so many more civil engineers in the future than we actually have today. We actually don't have enough civil engineers to fill the openings that are currently in the marketplace today. So if you've got a kid who's got a science mind, and he just loves, or she just loves building things, this might be an area of science that they might be interested in. So if you'd like this and you want more, go to my website, www.superchargedscience.com/easy. Like, wow, that was so easy. She just like taught my kids for me. I didn't have to do a thing. My kids come back, teach me science. They're totally responsible for their education. Because honestly, all you have to do is set your kids up and they are good to go on their own. Most parents skip science when they homeschool because they don't either have the time to do it or they just don't feel like they've got a science bone in their body. They like the know-how to really do a good job at it, so they just skip it. And I'm telling you, there's a better way. So if that's you, you definitely want to get on board. You can try the first 30 days risk-free. Try it. If you like it, great. If you don't, no problem. You get a full refund. There's nothing to send back. It's got a full unconditional happiness guarantee with it within the first 30 days. So you can try that now. And that reminds me, civil engineering specifically, if you just want the civil engineering course, there is a website for that. Let me show you where it is. You want to go to superchargedscience.com. Here, let me do it for you so I can show you. Give me just a second here. Let me put it on the screen and show you my slide. Here we go. Go to superchargedscience.com. This is superchargedscience.com. There's me. And you go under programs and you go under single topic science curriculum. And you click on that, and each of these is a single topic. So if you're only interested in civil engineering, you can click on civil engineering here, and you can simply buy the entire civil engineering course. And so you can get that online. Now, if you'd like to do all of these courses, then you want to do the online science program. I don't think the online science program includes civil engineering. I think here, let me go back up. civil and aviation and marine biology, these are add-on courses. So these are above and beyond. So if you like the civil engineering and you want to do more like it, you can get it just from the Supercharged Science website. But I encourage you to try the online science program because you could just try it risk-free for 30 days. Try it. If you like it, then you can dive in more and get more of these add-on courses. Okay, I hope this has been helpful. I hope you've enjoyed it. Let me know your feedback, what you liked, what you'd like to see more of. I'd love to hear back from you. Also, let me know how it's working for your family. I encourage you to join our Supercharged Science family where we do real hands-on science with kids, and it's very interactive. Kids that have questions talk to us all the time, and we get those questions answered, so you're never stuck or worried about, like, how am I going to find a science answer to that? I mean, how many times can you ask a textbook a question, right? Not very easily. But with an online interactive program, me and my team of engineers and scientists are constantly working with kids. So this is an awesome win-win situation. So we have mentors and we have kids and we have everybody that just is crazy wild about science. So if you'd like to join our science family, go to www.superchargedscience.com/easy. Like, wow, that was really easy. And I look forward to seeing you next time. Thanks everyone, and have a wonderful afternoon.